Hello everyone and welcome to this comprehensive presentation titled C++ program to implement B trees using linked lists. In the next few slides, we will explore what B trees are, why they are crucial in computer science, and how to build them from the ground up using C++. We will break down the implementation step by step, analyze each part of the code, and help you gain a solid understanding of how B trees work internally using pointers and dynamic memory allocation. Before diving into the code, let's understand what a B tree actually is. A B tree is a specialized data structure used to store sorted data in a way that allows searches, insertions, and deletions in logarithmic time. Unlike binary trees where each node has at most two children, B trees are multi-way trees, meaning each node can have more than two children. This makes them ideal for systems that read and write large blocks of data like databases and file systems. One of the key characteristics of a B tree is that all the leaf nodes are at the same level, ensuring balanced performance for every operation. Let's break down the structure of a B tree. It is defined by a parameter known as the minimum degree, denoted by the variable t. A node can contain at most twice t minus 1 keys and up to 2t children. When a node becomes full, it splits into two nodes and a key is promoted to the parent, maintaining the key tree's balanced nature. In our implementation, we use two classes, B-tree node, this represents each individual node, and B-tree, which acts as the controller that manages insertions and traversal. With this understanding, we now begin exploring the implementation details. This slide presents the structure of a B-tree node in our C++ implementation. Each node includes the following: an array of keys to hold the actual data, an array of child pointers which point to other B-tree nodes. This forms a linked list structure. A Boolean flag leaf that tells us whether the current node is a leaf. An integer n to keep track of how many keys are currently stored. This structure allows every node to dynamically manage its contents and connections to child nodes. The constructor initializes all the key components of a node. It first sets the value of t, which is the minimum degree. It that initializes Boolean flag leaf to indicate whether the node is a leaf node or an internal node. Arrays for keys and child pointers are dynamically allocated based on t, making the node flexible in terms of size. Finally, the number of keys n is initialized to 0. This constructor is critical as it sets up the infrastructure needed to build our tree nodes dynamically during runtime. Inserting a key into a P tree follows a specific process. First, if the tree is empty, a new node is created and the key is inserted directly into it. If the node already has the maximum number of keys, we split it into two nodes and promote a key to a new node. Then we insert the new key in the appropriate subtree. If the root is not full, the insertion continues recursively using the insert non-full method. This ensures the structure and rules of the B tree are maintained, particularly the rule that no node contains more than twice t minus 1 keys. The insert non-full function is the heart of the insertion process. It checks whether the current node is a leaf. If yes, it finds the correct index and inserts the key in sorted order by shifting larger keys to the right. If it's not a leaf, the function determines which child pointer to follow. If the selected child is full, we must split it before inserting further. This approach ensures that we only ever insert into non-full nodes, a key invariant that helps maintain the tree's structure. Node splitting is a crucial operation that maintains the balance of a B tree. When a node reaches its maximum capacity of keys, it's split into two. The middle key is promoted to the parent, while the left and right portions form new child nodes. The split child function handles this. It creates a new node, copies the appropriate keys and children into it, adjusts the parent's key and child pointers, and updates all counts. Without this operation, the B tree would never remain balanced and could degrade into a linear structure. The traversal of a B tree is done using an in-order traversal pattern. We recursively go through each child node, printing keys from the left to right, which results in the output being in sorted order. This is important not just for verifying the integrity of the tree, but also for operations like range searches or exporting tree contents. It's a simple yet powerful demonstration of how B trees maintain order while staying efficient. The main function demonstrates how the B tree works in practice. We first create a new B tree object by passing in a minimum degree, for example 3. Then we insert a series of integers such as 10, 20, 5, 6, 12, and so on. After all insertions are done, we call the traversal function to print the tree. The result confirms that the keys are stored in ascending order, verifying the correctness of our insertions and node splitting logic. Here's an example to visualize node splitting. Suppose a node already contains the keys 10, 20, and 30, and now we try to insert 40. The node exceeds its key limit, so the middle key 20 is promoted to the parent. The node is split into two, 10 and 30, 40. This operation helps prevent node overflow and keeps the tree height minimal, ensuring efficient performance. After inserting all keys and performing necessary splits, we run the traversal function. The output you see here lists the keys in ascending order 5, 6, 10, 12, 20, 30, and so on. It confirms the B tree is functioning correctly, maintaining balance, enforcing order, and storing keys across multiple nodes as expected. To summarize what we have learned, B trees are an essential data structure when it comes to managing large sorted datasets. They are efficient, balanced, and provide logarithmic performance for search, insertion, and deletion. In this session, we implemented a B tree using C++, designed the node structure using dynamic memory allocation, implemented insertions with node splitting, and used in-order traversal to verify correctness. This gives us a strong foundation for using B trees in real-world applications like database indexing and file systems. Thank you for your attention throughout this presentation. If you have any questions about the logic, the code, or applications of B trees, especially the use of linked structures and pointers, please feel free to ask now. I'll be happy to explain or dive deeper into any part of the program.